Hi class, it's Bill Berry here with a week 5 lesson from our Java 2 class. We are starting into some interesting territory when it comes to data structures, so this is a great start to getting into more detail on things that we can create ourselves. The array list, of course, we built on an existing data structure. We used the array as a basis, but with linked lists, we're kind of creating things on our own. So it gets kind of exciting and it's an important one, so let us get started with linked lists. First, we're going to remind ourselves about some of the good news and bad news about arrays. We're going to review has-a relationships and make sure we're clear on how those are created. And then we're going to talk about linked lists and look at several of the algorithms that are kind of key, essential for those, and look at how they're created. We're going to see that in essence these are actually very simple data structures to create. They're very powerful, but very simple at the heart of them. So arrays. Good news and bad news. Let's remind ourselves. First, with an array, all of our elements have to be of the same data type, right? With Java, we have strongly typed data. When you create an array, you have to say what's going in there. Another thing that's good here that we should add to the list is that arrays can work with primitive data type. We're going to see that now when we get into linked lists, we're probably not going to want to do that. We're going to want to stick, as we did with array lists, with objects, but that's another thing that we should probably add to the pros list. They are random access, right? So very fast. If you want to get at any particular element in the array by its index, you can get there in constant time, right? No matter how far you want to go down the array, it's the same amount of time to get there. So super fast access. Now, if you have to go search for something, that's a different matter. That's something that we can consider binary searches depending on the sort order, blah, blah, blah. But in terms of random access, super fast. The bad news about an array is that they are fixed size. So when you go to create the array, you have to tell it how big it is. And if that's not enough, as we saw with array lists, you've got to go and create another array and copy over the data. Now, we can be smart about that, but it's still a fixed size, right? You still had to create that thing at runtime the right size. Also remember, it is a big block of contiguous memory. Right? So when you go to allocate an array, it has to go find that memory. If you ask for 1,000,000 items in your array, it's got to go find something that's long enough and wide enough for all of the data that it's got to hold in one contiguous block. The other thing is arrays don't make it very easy for us to add or remove things in the middle. So if we really want things to stay in order, we have to shift things around. We have to add things in the middle after shifting things over, and if we want to remove, we have to shift things back over. So it's kind of a hassle, not really made for that kind of operation. What we're going to see with our linked lists is the fact that they're kind of the reverse of all of that. Right? They are going to be the same elements, the same type. That still applies. Random access doesn't apply. Super fast, no. Fixed size, no. Contiguous memory, no. Harden to add and remove in the middle, no, turns out. So sometimes you want to use linked lists because they are perfect for the particular scenario that you want. Even though they don't have some of the good news here, they also don't have some of the bad news here, and sometimes they are perfect. So that's why we're exploring linked lists, and we'll learn how to create and use those. So now let's go and take a quick look at our has-a relationships and remind ourselves of how those work. Remember that we have seen has-a relationships for a while. You created these probably in your previous course in a simple way. For instance, we had the idea of, in one of our projects, the fact that we have an airline. On that airline we have a seat. With that seat we have a customer confirmation, and with that customer confirmation maybe we point to a customer. We had something sort of like this, but you can see the idea that each one of these has a relationship with the other. Now, how do we do those? Remember that has-a relationships are created very easily. All you have to do is have a reference of the proper type. This test seat, the data type of that static type is a seat, right? And it refers to something that is of seat data type. The seat has a customer confirmation. The data type of that is a reference to a customer confirmation. So to make a has-a relationship is very easy. You just have to create a reference. Right? Make a variable that refers to the thing of the right data type and then point it to something, or point it to null if it doesn't have the something in question. The other thing is we learn how to navigate those relationships, which is especially easy if we have an object diagram like this. For instance, we could say If I want to get this customer's name and I'm way over here, I could say test seat dot get customer confirmation, assuming we have a get method for that, dot get customer dot get name. So every time you use these dots, remember the dots are important because they navigate, they drill in, and when you do the dot, it's going to follow that thing and let you drill into the next, right? So as soon as you mention test seat, you've navigated this arrow, then you can do a dot to drill into the object you're on here, which gets to here. You can do a dot to drill in here. So we're used to navigating these relationships. We have the general idea of how you can move around in those things, right? So the question that we come up is, do we have to have objects with different data types in order to use a has a relationship? Here, the test seat points to a seat, the seat points to a customer confirmation, which points to a customer. Do these have to be data types in order to make this work? And the important answer that is the basis for a lot of what we're going to do this quarter, the answer is no. It is not critical for us to have different data types in order to express has a relationships. Let's look at a possibility. What if we have student relationships like this? Each student has a study buddy, right? And that study buddy is a reference to another student so that we can find out the study buddy of this student, right? No big deal, it's just a reference, and we can do anything with references. That's the power, that's how we're going to build all this stuff. But it's okay if the study buddy points to another student. In fact, look over here at the data types. Study buddy is in fact a student reference. Even though we're in the student class, we have study buddy with a student reference. When you do get student or get study buddy on that particular object, you're getting back a student reference. When you want to set the study buddy, you pass in the buddy, which is a reference to a student. So you're still speaking in object references, but you're simply referring to another student. So we aren't going to get freaked out when we see that's a student, but this is also a student. Not that big a deal. The data type happens to be the same here, but it's really not a big deal. And we can do anything we want with these references. For instance, Lupe's study buddy is Chris, and Chris's study buddy is Lupe. It's okay that Lupe points to Chris and Chris points to Lupe, because if you want to ask who's Lupe's study buddy, you get back to Chris, right? If you had groups of them, you could imagine Chris pointing to Lupe, Lupe pointing to Pat, and Pat pointing back to Chris. You could have a cycle, right? You could actually have a loop of these, so you can go through and find all the associated study buddies. And then the question is, how do you not go around in loops forever and know that you got back to the beginning? Well, that's another problem for another day. But basically the idea here is you can have the same data type pointing to another object of the same data type. There's no rules against that, and that is going to be the basis for how we build linked lists. So let us move forward and talk about that. Linked lists are extremely powerful. They are data structures built on references. They really couldn't be simpler in terms of their construction, but they make us think a little differently, and they make us make our brains do some interesting stuff in terms of how we write our algorithms, because they're going to be different than we worked with arrays. So the analogy here is, what if we had a student roster? So if we wanted to think of this, think of a student, and each student has a hand that can point to another student. Right? Every student has a name and can use their hand to point to another student. And if you're not pointing to another student, you just point to the ground, right? We're going to consider that null. So we can look at different scenarios where we say, hey, to make the roster, I take one student and I raise their hand and I point to the next student. I take that student's hand and I raise it and I have it point to the next student, and that, et cetera, et cetera, et cetera, until every single student is pointing to the next student in the roster. And then the very last student, whoever that happens to be, maybe sitting in the last row, I'll have them just leave their hand pointing at the ground. And therefore, we have a linked list of students. Each student points at another student. And then the only thing I have to do is I have to point at the first student. We have to know how to get to the first one, right? So I have to say, hey, the students start here. So what are the scenarios that become interesting here? Well, what happens if a student in the middle stops pointing, right? They get tired and they put their hand down. What happens to every student that they're pointing to and everybody after? Well, they're not in memory anymore, right? They're going to be garbage collected, so off they go, right? What else? How do we add someone in the middle? Somebody comes in the middle of class and I say, oh yeah, you need to be in the middle. How do I include them, right? How do I get somebody pointing to them and them pointing to somebody? How do we work them into the list? We're going to look at that. What if someone says, hey, I've got to leave early today? How do we extricate them, pull them out of the list, but not lose the pointers, not have everybody garbage collected? So these become the essential thoughts here of how do I make sure that we are pointing correctly? How do we make sure that we are not losing anybody in the deal here, right? Everybody has to be pointed to. And last, another one to think about is how do I clear it, right? What if I want to just clear the list? What happens? How do I do that? Well, that's super, super easy. So let's look at a couple of the key concepts and terms, and then we're going to start looking at the scenarios and looking at the code that implements them and all of that. So let's just look at terms before we end this video. First term is the concept of a node. When you worked with a linked list, just like any other collection, you think of things as elements, right? Each of these elements is going to be called a node. The nodes are going to be identical in data type, right? Because that's how data structures tend to work, right? We want everything to be of the same data type. So these are going to be typically called nodes. Each thing in the list is going to be a node, right? What does a node contain? Well, nodes typically contain two parts. They're not just data, though they have a data part, right? So there's typically a data part. Often that's a reference to an object. Could be a primitive if you're building something like that. And then they also have a reference part, right? So just like the students, each student has a name, but they have an arm raised pointing at the next student. That's the reference. That reference is often called next. That's just a convention. It's not a magic word. It's just a typical word. So every node has a data part and a reference part. You could have more stuff if you want, but those are the two parts that are most typical. Also typically, those are public, right? So the next reference and the data reference are public. Now that's unusual because mostly with our classes we use private data. But remember that the node is going to be a concept that is used strictly by the list itself. This is not really going to be used for outside parties to talk to. We're going to have the client data talk to us in data. If they say, I want to add this student to the list, they're going to give us the student. They're not going to create a node. So where typically we would have client code pass us references to things, we're not typically with our nodes, right? They're going to pass us the data part. They're not going to pass us nodes. So while it seems odd to have them public, that's typically the way they go. You don't want to have to navigate get methods and set methods for these things. It just makes your code ridiculous. And we're going to see that we have clever ways to make those things internal anyway to make sure that we have control over our nodes and that nobody else is any the wiser, because we really don't want them to mess with our stuff, right? We want to keep that sort of more private. All right, now the other thing that we have to do, remember I said I have all these students pointing to each other, that's great, but somebody has to know where the first student starts. So you have to have some sort of reference that's not a node that points to the first element, simply a reference. Typically, those are called something like list or front or head, right? There's sort of head of the list, head of the line. So one of these is a fairly typical term. You'll see front. I'll use head just because I've been using that a long time. The head of the list and the tail of the list is something that I learned many years ago, but often you'll see front or list. Doesn't make any difference. You just need a reference, right? Because you got to start somewhere to get to the first student. The other thing is, because each thing points to the next thing in memory, all of those are maintained. The garbage collector won't come in and take away your stuff because as long as somebody cares, right, as long as somebody's giving love to another object, which means pointing, caring about them by pointing to them, those objects are safe in memory. So you have to be careful not to drop one of those pointers. If you make one of those pointers point to null accidentally, then certainly everybody else in the list goes away. They're in jeopardy. But as long as everybody points and you do the pointer movement carefully, everything's kept in memory, no garbage collection, and everything's good. Last, we're going to learn to move through the list, right? We're going to learn to navigate, which you can also talk about as traversing, right? You've got to walk through the list. So you need to search for things, you need to find all of the things, you need to see how many things, you have to list the elements, whatever. We're going to move through the list. We're going to traverse through the list. So at this point, one of the things that we'll look at quickly is sort of the navigation, just to make sure we're clear. This hasn't changed anything about how hazard relationship work, but now we're going to think a little bit differently because we're going to see a lot of .nexts in the world, right? So let's look at how we would write code for things like this. We're over here, just for practice, we're way over here in this roster list. And what happens if I want to get the first student's name? Right? So how would I do that? Well, I have to start with front. You always have to start here because that's the only thing this knows about. So it has to do front, which navigates to here, dot, and then I have to ask the student their last name, which would be something like get last name. Right? So remember, the data reference itself, internally the node is going to be good, but in this case, in this case we'll do front and then we'll do dot last name, right? So in this case, because these are public, we don't have to use the get methods, right? We said this data is public, this is public, this is public, no get methods, right? So I misspoke there. So we're going to do front, and that navigates to here, then we do dot, and then last name, which is public. So that's how you get to the first student's name. How about the second student? What if we want to pull out Barajas here? Front, dot, next, dot, last name. Front, dot, next, dot, last name, right? So far so good, making sense. What about the third student's last name? Front, dot, next, dot, next, dot, last name, right? So you can keep navigating that way. Now we're not going to navigate, like you're not going to go through the whole list that way, but I'm pointing out to you that it is okay and perfectly valid for you to use a bunch of .next, because remember, when you say here front, you are here. When you say .next, you've already followed this reference and now you're here. And .next again follows it again. So it's okay to have stuff that looks like this. It's a little mind-boggling at first, but it's perfectly valid to do that. What if we were trying to access a fourth student? What if we tried to do .next, .last name over here? Well, .next here is valid, right? .next points to null, but you better not put a dot, right? This is the problematic point here. .next was fine. That points to null, but as soon as you say .last name, you are dereferencing the pointer, right? You're trying to follow and use something with that pointer? Because now you're getting a null pointer exception. You're going to get really used to these things as you work. Now, again, we're not going to really find all these things by walking this way. This is impractical. We want to do this with loops. But I just want to get your brain under the impression that we're going to use a lot of navigation and we're going to say .next and sometimes multiple times depending on what you're doing. You got to be able to follow these things. And again, a particular diagram like this, an object diagram, can be very, very useful. We're always drawing pictures. When you're writing linked list algorithms, you're going to be drawing pictures because you need to think through carefully how to do things, how do you know you're at the end, etc. So object diagrams, if you didn't like them before, you're going to want to start using them now while you're working on these algorithms. And again, you're going to get very, very used to null pointer exceptions because it's so easy to do these things wrong and dereference at the end when you shouldn't, etc. So you're going to get very familiar with these. If you don't know how to debug, this is going to start killing you here, right? Because you're going to run into this stuff a lot and you'll want to debug to find out where am I, why did I go too far, etc. Okay. A quick note on testing. When you're testing these algorithms, and I highly recommend that you write some of these things for yourself. I know that you can go find code on the internet. I know that you can Google it or Bing it or Stack Overflow it and you can find these things. But this is a critical thing for you to think through by yourself. And when you go to test your algorithms, you're just going to get them wrong a lot of times at the beginning. You'll have something you think is going to be good and it's not going to work in some scenarios. So test your stuff. Think about the fact that the list might be empty. If the front reference is null and the list is empty, that's a special case depending on how you're coding, and we'll talk about that. So make sure that whenever you're testing, you think about whatever it is that you're doing, what happens if it's at the beginning, what if it's in the middle somewhere, what if it's at the end somewhere, what if the list is empty. You got to think about those things, right? So keep in mind those ideas when you're testing your code. So what we're going to do next is we're going to start talking about some things to keep in mind when you're coding, but I think this is a good place to stop because this video is getting long. So we'll just say that our testing slide is our last in this set. We're going to start thinking about the coding aspect of this and what are some general ideas that we want to have, general concepts when we're starting to code linked lists and general precepts so that we can make sure we're coding and thinking correctly. So let's stop the video here. Thanks for watching this one and continue on, and we will keep talking about linked lists and look at the algorithms and look at the code next.